Okay, here we go with vectors 2. So we're just going to move on. Before we were doing solving all the vectors in the plane as that, and that's fine, but now we're going to get a bit more into the vector algebra. Just get myself on this. There we go. Okay, so we can have vectors anywhere in the plane. We've been putting them on the origin to solve them, and that's a pretty common thing we're going to do quite often. You can also have vectors that are in 3 dimensions. So when I do illustrations for this, I'm going to kind of flip into 2 dimensions quite often because it's easier to draw, especially in this, but you can totally pull this into 3 dimensions and we will. Okay, so let's look at this vector, and we have a vector CD here, and this is a free vector. It's not tied to the origin like AB is. Now, CD can exist anywhere. The rule is that when you go from C to D, you must always go 5 right and up 2 to get there as you move from C to D. And we'll talk about position vectors on the next slide, and that's what AB becomes. So something that starts at the origin and goes to a point that will always be 5 right, 2 up, kind of has the same direction as CD. Okay, so let's put another vector CD, and we're going to start it at 2, 1 here, and we're going to go to 4, 6. So 4 and then up 6 here. Okay, and it's going to be terrible because I can't draw on this thing yet. Almost made it. Okay, so here's CD. Noticing that we always start at the first letter and then we end at the second letter. Okay, so I want to move this vector. I want to have its tail on the origin and make a position vector. I'm calling it OP because P stands for position. I mean, it's really up to you what you call it. O, obviously, for the word origin. So what do I need to do? I'm going to have to go 2 units to the left, and I'm going to have to go down 1 unit. Okay, so it's just going to take your point C. So always looking at your original point, whoops, and seeing where that ends up. When you do that, your original point, your initial point will go 2 left, down 1. So where's my other point? 2 left, down 1. So the vector OP that corresponds to CD and maintains the same position looks like that. And when you give that name, once you've made it a vector, once it's a vector and not just a chunk of line or it's just not a point, you can give it kind of a 1x2 matrix name. Okay? Okay, so let's make a couple of position vectors. So we're going to start at J, which is -3, 2. So it's here. So this is our initial one, and we're running to K, which is 1, -2. Okay, so our vector, tempting because this one's closer to the origin to draw it like this, but our vector is actually, our free vector looks like that with its tip here. Okay, so if I want to go and I have to take that point J and transfer it over to the origin, what am I going to do? I'm going to go 3 right, and I'm going to go 2 down. Okay, so we know it'll start here, and then let's translate this one. 3 right and 2 down. It's going to go just like that. So that's the position vector. Okay, and we notice that its endpoint is at 4, -4. So this position vector, and I'm just going to call it OP as well, is a vector like this. Okay, so you're just always thinking about the movement that you're doing to take the initial point and put it on the origin, and then the end of the vector will behave the same way. Okay, what if I give you a point, -5, -3? This is M. And what's the position vector for a point? Well, that's easy, right? You're going to start at the origin and go to point M. So the position vector, I'm going to call it this. Same values, matrix style brackets. Unit vectors. So unit vectors are vectors that have a length of 1. And they can go in any direction. The three most important ones, I'm going to do a 2D model here as well, are I for, oh my land, terrible, I for x, and j for y, and k for z. Okay, so I'm going to pretend these are all like 1 away. So there's +1 and -1 and -1, and this is just a 2D Cartesian plane. All right, so if you want to have a unit vector, it's always going to hit, it's going to have a magnitude of 1. It's going to be 1 long, but it kind of messes with what the endpoints will be. So let me try and change colors here. So if we have our I, always looks like this, and it goes, in this case, oh sorry, no, this is j. My bad, my bad. Okay, so this is j, switching it over. That's the unit vector j. And this is our unit vector I. Okay. My problem, and k would do the same thing, but suddenly you're going to have 3 digits and all there, is what about random unit vectors that aren't the rectangular ones, the perfect ones that go on the axes? Well, this is a unit vector too, but there's its coordinates and I don't know what those are at this point. So how can we figure that out? We can take any vector and make it into a unit vector. So let's say we have one, and I'm picking these for a reason, a random point here, which is 3, 4. And there's a vector, a position vector running from the origin to 3, 4. I'm just going to add some extra decorations here, and maybe a little bit of this. So we know that this is 4 high from the origin to our point, and that we know that this is 3, which looks like 13 now. So I'm going to call this point Q. All right, so what's the magnitude of vector Q, OQ? And notice, I'll talk about this in a minute, I'm putting more of these straight lines here, and in this case they're going to represent magnitude, and we'll bring it up again. Well, it's Pythagorean theorem, right? If you have a side, a right triangle that you've created with a side that's 3 long and a side that's 4 long, the magnitude is just going to be the root of the 2 legs. Do that math, it's going to be 5. So that's great. So I've got my real vector now, but I want to turn this into a unit vector, and I want to know where that's going to end. Like, I know it's going to be 1 long, but it's not going to go to here because it's not going to get that far. So it kind of has to be on this circle. Please let this work. Like this. And I want to know the coordinates of the endpoints because then I can describe that unit vector. Well, I need to take my 5 or 3 triangle and turn it into a triangle that is the same. It's a similar triangle, but it has to have that r value, or the hypotenuse, whatever you want to call it. It has to be 1 long. So basically, how do I take 5 and make it into 1? I multiply it by 1/5. So for my y direction, to scale it, I have to do the same thing. For my x direction, to scale it, I have to do the same thing. Okay, so our unit vector ends up being and that tells us the direction really of OQ, but in a magnitude that is only 1. And when you do that, you call it normalizing. Here's the formula for normalizing a vector. I mean, this one's in 3 dimensions, which our second question will be, but it's the same as saying if you have 2 dimensions, vector in the y, x, and then over the magnitude of that vector. So Pythagorean theorem works in 3 dimensions as well. So if I'm looking at m here, and I want to find the unit vector, well, I have to first start by finding the size of m. Okay, and if it's this, that means it's moving, left or down, up 2. So we're just going to use those values. So once again, Pythagorean theorem. Do the math. Okay. So that's root 20. And we look over at this formula. So what we're just going to take is we're going to be like, okay, we need to have our vector. And we need to divide it by the magnitude. And you can write this unit vector that you've made like this if you want. Now, if you're fancy with your radicals and you want to simplify your radicals or rationalize your denominators, that's absolutely fine. I'll accept that as well. I guess it doesn't really matter. You'll see whether it's one of the answers on the test. I have no longer have any say in that, but this is correct as well. Okay, so let's look at Q. Start by getting the size of Q. And it doesn't matter that we have 3 dimensions. Math is the same. Okay, so that's 4 plus 9 plus 1, root 14. And same thing. Oops, normal 3, negative 1 over root 14. And this can sometimes be left out in front. It can be incorporated. Just look for the answer that has the same values. There we go. We have normalized Q. We have found its unit vector. Same here. We have normalized M. We have found its unit vector. All right, so all these kind of non-rectangular unit vectors are fine, but when we describe vectors, you're also going to often see I, J, and K, which is just putting it in terms of those rectangular things. So if I had a vector M here, which kind of says, negative 1 in the x-axis, 2 in the y-axis, 7 in the z, you can describe it by just translating that and putting the I, which makes that negative 1, and then we have a positive 2j, which is our y direction. Okay, so same difference, okay? So it's like doing this math, taking your value that you see in the vector description and putting, this is I, right, in disguise, with an extra, this is j, and this is k. And I mean, honestly, if you were to incorporate these back in, you're just kind of doing multiplication of a scalar times a 1/3 matrix, right? So when you do that, you end up here, and then guess what? If you have 3 1/3 matrices or vectors, you can add them and get back to where you started. Okay, so not that useful to do all that math to end up where we started, but pretty useful to put things in terms of I, J, and K. So if we were to try one on our own, if I just gave you anything, let's say it's T, and let's just make up some numbers, oops, that are gross, and you're going to be like, okay, that's like negative 7 in the x direction, positive 32 in the y direction, and negative 20 in the z direction. Same difference, just another way of expressing it. So we can do math, and this is so similar to how we did it with matrices, right? If we had A was this kind of matrix and B was this kind of matrix, now do this math for me. So this works out the same way, but I'm just going to start by writing them IJK style. So we have M. So I'm looking at M is 3 in the I direction, 4 in the J direction, -1, and I left the 1 there for some reason, in the K direction. We're going to add it to 2 times N, which is -2 in the I direction, 1 in the J direction, so this time I'm leaving it off just to be confusing, and 2 in the K direction. All right, and then here we go. Boom, distribute it, right? Same thing you did with anything else. This kind of becomes like basic algebra. So we have 9, 3 times 4 is 12, and 3 times -1 is -3. And then we're going to do the same thing right here. 2 times -2, and 2 times 1, and 2 times 2. At this point, it's like you had 3 different variables. You're going to gather like terms. You can add these two, 9 minus 4, 5 in the x direction, 12 plus 2, 14 in the y direction, and -3 plus 4, 1 in the k direction. Sometimes it's easy to do the simplifying before you go to the IJK version. Okay, so here I'm going to start by simplifying with n and m being left alone. So I have 2n minus 4m plus 3m minus 4n. So don't turn everything into this. That's way too much work. Simplify. Gather your n's. 2 minus 4, -2n. Minus 4 plus 3, -m. Now, bring in the IJKs. Okay, so we said n was -2i plus j plus 2k, and m, I'm just going to leave it with the brackets instead of being fancy with changing my signs. 3i, because I know myself, plus 4j minus k. All right, so I'm going to distribute to all 3 again. -2 times -2 minus 2j and minus 4k. And here I'm going to distribute that negative, and it'll just change the sign of everything. So minus 3i minus 4j plus k. Okay, and we're going to have 4 gathering like terms. The i's go together. 4 minus 3, plain old I, 1i. And then 2, -2, -4, minus 6j, -4, plus 1, minus 3. Okay. All right. Done and done. So what's next? Okay, so this is just kind of, we touched on this already, but this is me going back to vector magnitudes. So those straight lines no longer mean, oh my goodness, a determinant. I've already forgotten what they mean with matrices. They now mean the magnitude, the size of the vector. And we are using Pythagorean theorem to do this. And we can just keep adding in extra dimensions. That is fine. So if you have your vector as indicated by those things and you want to find the magnitude, you're just going to take the x, square it, add it to the y, take the root. Okay? And we've seen this already, so let's do some math with it. Okay, so we have a point. This is not a vector, it's just a point. It's got the normal kind of brackets around it, and we want to find the magnitude. So first of all, let's describe vector OR, because we're probably going to use that on a different slide. Going from 0, 0 to that point, this is its description. And now we have to find the magnitude. I got excited and tried to go to the next question. So we're going to put that straight line brackets to tell that we're doing the size, and then right back to finding that scalar. Okay, and you should get, when you do that math, hopefully, although that. Same deal. If we have a point S, that means going from the origin to S. And likewise, a magnitude, sorry, that should have been an S. Whee! Don't trust my eraser. Same math, same math. And hopefully when you do on that math, you're going to get 29, and you just leave it in exact form. That's fine. Okay, let's ramp it up a bit. Oh, sorry. That came through from my slideshow. We'll just scratch that out. Okay, so let's think about RS. So I'm going to draw these as two-dimensional vectors because that's what I know how to do. And we'll just pretend there's another dimension going up. So let's say this one is R, and this makes this OR. And let's say this one, put that is S. And you can solve this with analytical geometry too, but I'm just trying to do it vector style. And we're doing that. And we want to know about RS. So we want to know about the vector that starts at R, and this is a little bit important in terms of science, and goes to S. So that is this vector. And if we think back to vectors 1, we knew that if you were looking for the resultant, right, you were adding tip to tail. So I have a math statement here that is basically saying that OS is equal to, and I'm not dealing with magnitudes yet, I'm just dealing with the whole vector issue, the sum of OR plus RS. Cool. So if I want to find RS, what's my math? A little bit of rearranging. So that's what I have to do. Okay, so OS we said was and OR, and we remember that these vectors behave like 1/3 matrices, and we can just do the x's minus the y's minus the z's. We don't have to put it in IJK, we can just leave it in this format and do the math. So what we're going to have for our points, for our x, we'll have -2 subtract 3. This x subtract that x. For the y's, we'll have 4 minus -5. And for the z's, we'll have -3 minus 2. So I'm moving into this place, but that's life. And describe this vector. It moves from R to S in this kind of direction. Excellent, but I wanted the magnitude, so don't forget, good job, but you got to finish it by getting the magnitude. So I'm going to take, and I'm going to go over here, squared plus 9 squared plus -5 squared. Okay, and I get 81 plus 50, and I should have root 131, hopefully, as my magnitude. Okay. This one, they want a magnitude, but they want us to do some math first. So we're just going to do it like we did in the other questions. You're going to take 3, and you need to multiply it by OS. and you're going to subtract 2. You're going to multiply it by OR. 2. Okay, so we have negative 6, 12, and I'm just doing the same distribution. I'll do it for both ones. For this, I'm going to leave the negative. You could bring it in, but that will change it to a plus. I'm going to leave the subtraction and just distribute the 2. But it will work either way. 2 times negative 5, negative 10. And 2 times 2 is 4. Okay, and now I will do the math. So negative 6 minus 6 is negative 12. 12 minus 10 is 22. It's like 12 plus 10. And negative 9 minus 4, negative 13. Oops. So as we move around, these are the x direction change, the y direction change, the z direction change. But once again, I want the magnitude. So if we want to get the magnitude, we have to do all the gross math. Okay, there we go. And that's all I'm going to cover for vectors 2. We're going to get into the big things, the dot product and the cross product in the last slideshow, vectors 3. So hopefully I'll be recording that shortly.